going to go over some examples of small sample hypotheses. And for the larger samples, we can use a shortcut to find the approximate probabilities, but for very small samples, we need to use the exact probabilities, and to do that, we will be using a tree diagram. In this example, we have a sample of 3 patients, the proportion cured by a new drug, p hat, 2 out of 3, or approximately 0.67. It is known that the proportion of cured by the old drug, p of 0, is 0.6. We want to test the following hypotheses at the alpha equal 0.05 level of significance. I like to call it the level of doubt. H naught, p equal 0.6, the new drug is not better than the old, versus HA, p greater than 0.6, the new drug is better than the old. So just based on this small sample, it looks like the new drug has a somewhat higher cure rate than the old drug, but that could have happened by chance, and we want to know how strong the evidence is that the sample provides us that the new drug is better than the old drug. So we want to first check whether n times p0 is at least 5 and n times 1 minus p0 is at least 5. If it is, we can use the shortcuts, but if not, we have to compute the exact probabilities. So n, our sample size is 3. P0, that's the null value, that's the value of p if h naught is true, is 0.6. 3 times 0.6 is 1.8, and that's not bigger than 5. 3 times 1 minus p0, 1 minus 0.6 is 0.4. 3 times 0.4 is 1.2, and that's also not greater than 5. So we need 2 yeses in order to use the shortcuts. Even if we had a yes and a no, we would have to use the exact probabilities. Some books use the standard n times p0 is greater than or equal to 10, but our book uses 5. But the bigger these numbers are, the more accurate the shortcut is going to be. Okay, so we want to use the binomial probabilities. The name binomial comes from the word two names, literally 2 names. Binomial variables have 2 possible outcomes for each case. In this example, each patient is either cured or not. And we will make a tree diagram to do this, to compute these binomial probabilities. And we set up the tree diagram as if the null hypothesis is true, and that each patient has a 60% chance of being cured, 40% chance of not being cured. Okay, so let's set up the tree diagram. Okay, so the first patient is either cured or not. And if H naught is true, they have a 0.6 chance of being cured. 1 minus 0.6 is 0.4, so they have a 0.4 chance of not being cured. And the second patient is also either cured or not cured. I'll just abbreviate this as C and N. It's cured, not, not. And the probabilities are the same, 0.6, 0.4, 0.6, 0.4. That's for the second patient. Okay, so there's 4, if you have 2 patients, there's 4 possible outcomes. They could both be cured, that's cured. First patient is cured, the second patient is not. That's the second path on the tree. First patient is not cured, the second patient is cured. That's the third path on the tree, or neither patient is cured. And then the third patient, the number, each time you add a patient, the number of paths is going to double. So we'll have 8 possible outcomes for 3 patients. So either cured or not. when you make the tree, be careful to line up the vertex with the letter that it comes from, so that it's clear that how to get from this point to that point. Okay, so the probabilities are going to be the same. So we're going to have 8 possible outcomes here. 0.6 chance of being cured, 0.4 chance of not being cured. Okay, so we want to multiply along the path, and we actually only need the paths where at least 2 out of the 3 were cured, because our sample size and our sample proportion was 2 out of 3. So we want all the paths where at least 2 out of 3 were cured. So the top path, all 3 were cured. 0.6 times 0.6 times 0.6, 0.216. So that's cured, cured, cured. I'll put CCC here. All 3 were cured. The next path, we have first 2 are cured, the last one is not, so it's 0.6 times 0.6 times 0.4, and I think it's 0.144. That's cured, cured, not. The third path, we have cured, and then not cured, and then cured. That's going to be 0.144 again. The next path, 0.6 times 0.4 times 0.4. We can skip that path. Let's skip that path there, because we only need the paths where at least 2 out of 3 were cured, because our sample proportion was 2 out of 3. So let's skip this path here. And next path we have not, and then cured, cured. So that's going to be 0.4 times 0.6 times 0.6, which is 0.144. So that's the first patient is not cured, and the next 2 are. Next path, we can skip again. We have not cured, cured, and then not cured again. We can skip that path because there's only 1 cured. Not, and cured we can skip, and the bottom path, nobody was cured. So we only want the paths where at least at least 2 of the 3 were cured. So if we add up these probabilities here, 0.216 plus 0.144 plus 0.144 plus 0.144, it gives us a p-value of 0.648. That's a pretty high p-value. Usually you want your p-value to be small. Usually less than 0.05. Because this means we have a 65% chance of getting a result this extreme if H naught is true. And so that's a pretty high chance of getting that. Sometimes it's helpful to make a little table. So we can put these paths in the table. The top path was cured, cured, cured. That was probability of 0.216. And then cured, cured, not. That was 0.144, 0.144. 0.144, and then the total of the p-value, just add these up. 6 and 4 is 10, and double 4 is 18, carry the 1, 1 is 2, 4 is 8, 1 4 is 5, and 8 is 13. Let's see. Oh, okay. We know we're carrying 1 here. 1 and 1 is 2, and 4 is 6, 10, 14. Carry the 1. 1 and 2 is 3, 4, 5, 6. So our p-value 0.648. And it's more than our desired level of doubt, which is 0.05. So we fail to reject H0. Sample does not provide enough evidence to say the new drug is better than the old drug. And our p-value, if you look at this chart here, is between 0.1 and 1. So the sample provides little evidence that the new drug is better than the old drug. Okay. Let's redo example 3a if the proportion cured by a new drug was 1 out of 3. Okay, so it's basically going to be the same tree, except now we want the paths where at least one was cured. Okay, so so again, it's basically doing the same tree we had before. Cured, not. That's the first patient. And cured, not. That's the second patient. And let's put the probabilities in. If H0 is true, each patient has a 0.6 chance of being cured, 0.4 chance of not being cured. Okay, third patient, either cured or not cured. The probability is again 0.6 and 0.4. Okay, so we want the paths where at least one is cured, because now in the second example 3b, our sample proportion, the proportion cured was 1 out of 3. So we want the chance where it was at least one cured. So anyway, 0.6, 10.6, 10.6, 0.216, and that's all 3 were cured. 0.6, 10.6, 0.4, that's the first 2 were cured, and the last one is not. Cured, not cured. It's also 0.144, 0.6 times 4 times 0.6. That's going to be cured, not cured. Next path, 0.6 times 0.4 times 0.4, again 0.144. Oh, no, 0.96. That'll be cured, not. And then we have 0.4 times 0.6 times 0.6 is 0.144. That's cured, or not cured, cured. And then we have 0.4 times 0.6 times 0.4, 0.096. And that's not cured, not cured, not rather. And then we have 0.4 times 0.4 times 0.6 again, 0.096. And that'll be not cured. Okay, and the bottom path we can skip because we want the paths where at least one was cured. So if we add these up, it gives our p-value of, let's see, we have 0.216 plus 3 times 0.144 plus 3 times 0.096. Try that again. 0.216 plus 0.144 times 3 plus 0.096 times 3. Yep. 0.945. Okay, so that provides even weaker evidence. It's a slightly higher p-value than what we had before. That's little evidence that the new drug is better than the old drug. Okay, so redo example 3a. If the proportion cured by a new drug was 3 out of 3, again we can use the same tree, but we only need the path where at least where all 3 were cured. Okay, so we can skip the other paths because our sample proportion is 3 out of 3. So we want only the paths where at least 3 were cured. Okay, so the first patient is either cured or not. Have a 0.4 chance of being 0.6 chance of being cured. 0.4 chance of not being cured. Second patient also either cured or not. Point 4, 0.6, 0.4. Third patient, either cured or not. So with 2 patients, we have 4 possibilities. They're both cured. First is cured, second is not. First is not cured, second is cured, or neither one is cured. Each time we add a person, the number of paths doubles. So now we'll have 8 possible outcomes. And they're either cured or not. And the probability is 0.6, 0.4, 0.6, 4, 4. Okay, so we only actually need the top path, 0.610, 0.610, 0.6, 0.216. That's all 3 were cured, and we can skip the rest of the paths. There's only one path where at least 3 out of 3 were cured. Okay. Okay, so our p-value is 0.216. So there's only the one path where all 3 were cured. Okay, so none of the examples gave strong evidence that the new drug is better than the old. Typically, with small samples, you're not going to get very strong evidence against the null hypothesis. And again, we can discuss the probability of type 1 or type 2 error. So again, either H0 is true or HA is true. Either we don't reject H0 or we reject H0. In this case, we did not reject H0. So it's possible we made a type 2 error. Or we might have correctly, or maybe it's just that H0 is true. It might have been correct in not rejecting H0, or we might have made a type 2 error. So that was that's about as much as I can say about this sample. This sample, with the small sample size, it did not provide strong evidence that the new drug was better than the old. Maybe the new drug was better, maybe it wasn't. And that concludes this presentation.